Hello, this is Math Jazz from Almost Cool. I am doing a math live stream today. We're preparing for exam 2 in my class, so we will go over some topics related to that class. But if you have your own math questions, feel free to put them in chat, or as it says on the screen, you can email them to me. And if you email them to me, I recommend if it's too complicated of a problem to write into chat, you should email it to me. I have my email pulled up. We can look at if you need to, you can write something down on paper, snap a picture of it with your phone, and then send it to me. Okay, so with that, we will go to our first problem. So I have here several problems from past semesters' midterms. So let's just start with this one. Okay, so we want to figure out which of these statements are true. So all functions have extreme values. That is not true. I'll give you a picture of why that's not true. So here is a function that has no extreme values. Oops. Alright. I'm switching to paint.net. Here's a function, no extreme values. We go up and down in both directions, no maximum, no minimum. Okay. How about if f prime of c does not exist? There we go. We'll see that. That's not cool. Okay, there we go. So if f prime of c does not exist, then f of c is not an extreme value. That is also not true. So we have function like this one. There's no derivative there because there's a sharp corner. However, the maximum is obviously at that sharp corner. Oh. Okay. Next one. If f is continuous on an open interval, a to b, then f attains an absolute minimum value, f of c, at some c in a to b. This is also false. So let's show an example of that. We have, well, let's just have an asymptote that drops down. Gosh. There we go. There is no minimum value between the points x equals a and x equals b. Let's say continuous. Let me check. Oh, f is continuous. That's okay. We'll just change this picture a little bit. Well, I guess we also have to move it up. There you go. Put it over here. Okay, so let's select this chunk here, delete it, and okay, we are continuous on the open interval a to b. A is the asymptote and b is on the other side. This function here is continuous on an open interval. However, it does not have a minimum value because it has this asymptote or it asymptotically approaches x equals a. Okay, so that one is false. The next one, if f has a local maximum or a local minimum at c, and f prime exists, then f prime of c equals 0. Okay. That is true. That is called, I think it's Fermat's theorem. But yes, it's a true statement, regardless of my ability to remember its name. So that one is true. The next one is all continuous functions have extreme values. Well, continuous on an open interval, and it has no minimum, so that means the second to last option is false. And then if f prime of c equals 0, then f has either a local maximum or a local minimum at c. Well, here's an example otherwise. We have function goes up like that. Here is a horizontal asymptote, but no max or minimum at the point c, f of c. Of c. Okay. Let's look at the next problem. What is the derivative of this? Let's copy that over to the other board now. We have sine squared of x cubed plus 3x. This is what we want to take the derivative of. So we get, we're going to use the chain rule here. Let me show you a technique for organizing the chain rule. I'm going to draw a t-table like this. My outside function is my squared function. It's the last thing I do if I were to plug in a value. If I plugged in some value into this function, the first thing I do is cube it, multiply it by 3, and then add those together. The next thing I do is whatever came out of this, I would do sine of that. And then the next thing I do is whatever came out of the sine, I'd square it. So my outside function is x squared. My next function is sine x. And my inside function is x cubed plus 3x. Once I've divided this problem into pieces that I can easily take the derivative of, power rule, derivative of sine, power rule again, I take those derivatives. 2x cosine x and 3x squared plus 3. From here, I'm going to, let me change colors. Here, I'm going to take this function, plug this function into it, and then plug this function into that one, like so. 2 sine of x cubed plus 3x. After that, I'm done with this particular derivative. Move on to this one. Let me pick another color. I take this function, and I plug this one into it. So I get cosine of x cubed plus 3x. And then I'm done with this function. Move down one more. Let me pick one more color. I multiply it by this, and I'm done. And that gives me my derivative via the chain rule. So I just write this out up here as my derivative. 2 sine x cubed plus 3x cosine of x cubed plus 3x. And 3x squared plus 3. That is my derivative. Okay. So, moving on to our next problem. We want to find the slope of the tangent line for this function when x equals 0. Okay, so with that, let me write my function f of x equals sine squared x over x squared plus 1 cubed x equals 0. There we go. So the first thing I want to do is find the derivative. Because to find the tangent line, you need to know the point where your line is tangent to the curve. And you also need to know the slope. So the derivative of a function is its slope. We'll take the derivative here. Now, we could use quotient rule here. That would give us an answer. But this looks like a fairly complicated function to take using the quotient rule. So what I'm going to do is I'm going to use logarithmic differentiation. So first thing I'm going to do is take the natural log of both sides of my equation. Natural log f equals natural log sine squared x over x squared plus 1 cubed. I'm going to simplify this as the natural log of f equals, my power 2 comes down in front as a coefficient, 2 ln sine x, close, and then everything in the denominator is a negative because division inside a log is subtraction outside a log. And this 3 gets to come down as my coefficient for the negative term, 3 ln x squared plus 1. So far, so good. After this, I'm going to take the derivative. The derivative of the natural log of f is f prime over f. The derivative of this side is going to be 2 times the derivative of cosine. Sorry, the derivative of sine is cosine. Cosine x on top, sine x on the bottom. And then minus 3 times the derivative of this is 2x on the top and x squared plus 1 on the bottom. Now, if I multiply both sides of my function, or sorry, my equation by f, remember f equals sine squared x over the cube of x squared plus 1. You multiply the equation by f on both sides, you get the derivative all by itself. So the derivative is going to be this. Okay. So let us move on.
Wells Fargo has the #1 mobile bank.
Whoa.
And it just got even better. So customers are settling up with each other. How does that matter?
Just ask Patsy. You should see my cross stitching.
Okay, sorry, had to mute my Twitch channel for a second. Okay, so let us move on to the next problem. Here we are. So the next problem is we want to find the limit here. We have the limit. Let's turn our ink black again. Limit as x goes to 0 of sine of 5x sine of 3x over 5x squared. Okay. So with this problem, what we're going to do is we're going to use a trick from one of the limits that we were supposed to memorize in this class. We are going to recall that the limit of sine x over x as x goes to 0 is 1. This is the key. So we can split this apart into product limits. First one goes to 0 of, I want sine of 5x over 5x. That's going to take one of these x's and the 5. We have one x left over. We're going to put that into a second limit. X goes to 0 of sine of 3x over x. What I want is I want this 3x to be balanced by a 3x down here. So I'm going to multiply by a 3 on the bottom. But if I'm going to multiply by 3 on the bottom of a fraction, I have to multiply by 3 on the top of a fraction to balance it. There's my 3 on top of a fraction. Okay, so I have both of my x's accounted for. 1, 2. I have my 5 accounted for here. Sine 5x is here. Sine 3x is here. And then I have a 3 that I added. But I also added it on the top of the fraction so it doesn't change anything. And now, this limit here, it goes to 1. This limit here also goes to 1. We have 1 times 3, and that is equal to 3. And that solves this limit. Now, if you're looking at this and you're saying, if we plug in 0, we get 0 over 0, we could have used L'Hopital's rule. That's absolutely correct. We could use L'Hopital's rule. And that would get us the correct answer. However, this way is easier in this case than L'Hopital's rule. So, let's go to our next question. We're going to find this derivative using implicit differentiation. So, our derivative is going to be y squared plus xy equals 4. We want to find our first derivative. So, we're going to use our implicit differentiation rules. That's going to give us 2y prime. That's the derivative of this first term. We have to use the product rule for the second term, so we get derivative of x times y is y, plus x times the derivative of y, which is y prime, equals, and the derivative of a constant is 0. Oh. Like so. So, this is our equation. Here's our implicit derivative. Now we need to solve for y prime. So I'm going to factor a y prime out of the terms that have a y prime in them. So we have 2y plus x. And everything that doesn't have a y prime, we will move to the other side of the equation. Like so. Now we get y equals, we divide by all of this stuff. So we can get y prime by itself. Negative y over 2y plus x. Now, we were originally asked to find the derivative. Oh, we were just asked to find the derivative. I thought we were asked to find the derivative at a point. However, it's good to know how to find the derivative at a point. We just plug in the x and y value of the point into this, and that gives us the slope of the tangent line. So let's say that we were asked to find, let's see. Well, this equation here, the point 0, 2 is on it. So we know that 0, 2 is a point on the curve. If we were told find the tangent line at this point for that curve, we'd just plug in this point into this this derivative and we get y prime at the point 0, 2 is equal to negative 2 over 2 times positive 2 plus 0, which is equal to, well, 2's cancel, we get negative 1/2. So our tangent line has a slope of 1/2. It goes through a point 0, 2. So here's our here is our tangent line. We get y minus the y coordinate equals the slope times x minus our x coordinate. This is the tangent line for this curve at this point. Okay. So let's look at a new problem. Okay, so we have here, if f of x equals this function, and I will write this function down now, have f of x equals x cubed minus 5x squared plus 4x minus 2 on this interval, 1 to 3. The mean value theorem guarantees there's a number c such that there are several statements here. So, but what we do know is that we're using the mean value theorem. So let's see what the mean value theorem actually does say about this function. So the mean value theorem says that if f is continuous on an interval a to b, in this case a is 1, b is 3, closed interval, and f is differentiable on an open interval a to b, in this case 1 and 3, then there exists c such that f prime of c equals f of b, which in this case is 3, minus f of a, which in this case is 1, over b minus a, which is 3 minus 1. So that means that f of c, which is 3x squared, minus 10x plus 4, this is f prime of x, equals f of 3 minus f of 1 over 2 at some point between 1 and 3. Let's figure out what f of 3 and f of 1 are. F of 3 equals 3 cubed minus 5 times 3 squared plus 4 times 3 minus 2. So we get 27 minus 45 plus 12 minus 2, which is going to be 27 minus 35. This 2 cancels with a 2, and then this 10 cancels with a 10. They're subtracting 35. That gives us -8. And f of 1 is equal to 1 minus 5 plus 4 minus 2, which is going to be 2, I think. That cancels to be -1. That cancels to be 0. It's -2. So that means that we get 3c squared minus 10c plus 4 should equal -8 minus -2 over 2, or -6 over 2, or -3. So let's look back at our statements to figure out which of these match the problem. So we have here, we know that there's some place where the derivative equals -3. That's what we proved. That looks like option 1 to us. Yes. Option 2 is also correct, but it's somewhere between 1 and 3. This statement is true. However, this one is more precise because the mean value theorem talks about a value in the open interval that has hard inequalities like this. The mean value theorem's conclusion is not a conclusion about soft inequalities like this one. Now, here's the thing, is if you know a number is strictly between or strongly between 1 and 3, you know it's weakly between 1 and 3 as well. Like, any number that is in here is also in here. But the other way around is what doesn't work. One is, C can equal 1 on this statement. C cannot equal 1 on that statement. So this statement includes this one, but not the other way around. Okay, so let's see. 3 is false. We know that f prime is going to be -3 somewhere, not 0. Let's see. So it turns out that f of c. We get a conclusion about f prime of c is going to be -3, not f of c is going to be -3. Because we know that f prime of c is going to be -3, and -3 is between -2 and -8. But we don't know. The mean value theorem doesn't say things about f, it says things about f prime. And again, this is a statement about f. We don't know that about from the mean value theorem. F prime is the subject of the mean value theorem. And the last one is a true statement, but it's just the definition of derivative, which again has nothing to do with the mean value theorem. So some of these statements are true, but the one that's true and actually has something to do with the mean value theorem is the top one. So that'll be our answer for this. Let's move on to the next question. This is an exponential problem. We don't do these on our exam 2s anymore, so I'm going to skip this one. Thanks to the viewers that are saying thanks in the chat. Okay, so here's our next problem. We have a cube that has the volume is increasing at 6 centimeters cubed per minute. So we have here EV ET equals 6. We have how fast is the length of an edge increasing when each edge is going to be 10 centimeters long. Okay, so I don't want to use E. E was a dumb choice of variable. I'm going to use X. Ooh, deleting makes things black. That's not great. There we go. Okay. Sorry, new program, still learning how it works. Whoa. How do I unselect? Okay. X equals 10. Okay, so what we know is that our volume, the volume of a cube is just the length of a side cubed. V equals x cubed. And now we're going to find our derivative. We take the derivative of both sides. So derivative of v with respect to t is dv dt. Derivative of x cubed with respect to t is equal to 3x squared dx dt. And then we plug in the information we have. X is 10, dv dt is 6. So we get we get 6 is equal to 3 times 100 times dx dt. We're going to cancel a 3 from both sides, cancel a 2 from both sides. That gives us dx dt is equal to 1/50th. Okay, so I want to stress the importance of taking the derivative first and then plugging in the values after. You see, when you plug in a constant and then take a derivative, the derivative will treat that constant as a constant, or it'll treat that value as a constant. So if I plugged in the 6 in this step here, if I plugged in the 6 here, that tells the derivative when I take it in the next step that volume doesn't change. Volume is fixed at 6. Okay? That's why, and that's not the case. We know from the wording of the problem that we have a cube that's expanding, and we know the volume is expanding. So by plugging in the value first, we've changed our situation. We have done the math for a cube that has no changing volume. It has a fixed volume at 6. And that gives us the wrong situation. So for these related rates problems, they'll give you a bunch of information. You want to use the information you need to set up the problem first. And then after that, you will want to take the derivative. And then after that, you'll plug in your constant values. Okay, so let's look at another problem. If you guys have any problems you'd like to ask me, you'll feel free to send them to me. Okay, so since I don't have any questions from you guys just yet, we will move on to our next problem. Here we go. This looks kind of scary, but it's just the quotient rule. So if we remember, the quotient rule is the denominator times the derivative of the numerator. So gx dx of f of x, so far so good, minus the numerator times the derivative of the denominator, that looks good too, all over the square of the denominator. Oh look, that's bad. Okay, let's find a new one. It's not the first one because it doesn't have the derivatives mixed, or the functions mixed properly. It's not the second one because denominator's not squared. The third one. The numerator in the second one is the same as the third one, so the numerator is good for the third one. Over the numerator squared. Well, that's wrong. So we keep going. This has a numerator squared. This is just patently wrong. Ah, Daniel Hutchings. Where did the dx dt come from in the top right? Sorry. There is a delay on this, the live stream. YouTube has a buffer. So I think you are looking at this question when I solved the volume of the cube. Let's go back. Okay, so I think that what you're talking about is this up here. And it looks like you cannot see my cursor. So let me just... You're asking about this. Here we go. This here. Okay, so the thing is that in this situation, when we're looking at this problem, we have a cube that's expanding with time, okay? So the input variable is time, and the output variables are the length of the side and the volume of the cube. So when we're looking at our volume equation, the volume equation has both the volume and the side length in it. But we're not taking a side length derivative, we're taking a time derivative. We want to know the side length, how fast it's changing in centimeters per second, or per minute, or whatever the units are. And so, since we're not taking a change of an x length versus an x length, you know, a side length versus a side length, we don't have our derivatives canceling like we normally do. See, in the normal situation, when we take a derivative, let's say we say f of x equals x squared is our derivative, our function to take a derivative of. We go, okay, well, the derivative, we're taking the derivative with respect to x, we get 2x. But what we always have meant, but never wrote, is dx dx. Notice that the top and bottom are the same here. And just like a fraction, when the top and bottom are the same, it goes to 1. But that's not the case here. Since our derivative is a time derivative, not a distance derivative, and our numerator is a distance, not a time. Since the top and the bottom aren't the same, they don't cancel. So that's where we get this dx dt coming from. Okay, so I hope that answers the question. Let us go back to, we were in the middle of the quotient rule question. Okay, so we have here quotient rule. I'm going to change my view just a little bit to make it easier to do this. There we go. Okay, so I think that we just figured out that the third option on this question is the correct one. No, the third one is wrong because it should be the denominator squared, not the numerator. But if we go down to the bottom, we have down, d up, minus up, no, up, d down, over down squared. This is the correct chain rule. Okay. Let's look at the next question. Is which of the following statements is incorrect? Well, this one here is a lot easier if you remember all of your derivative rules. I have to admit that I'm not very good at memorizing anything. So I usually have to prove these things for myself instead of relying on my memory. However, I think I can do these from memory. Just because we've been reviewing for the exam for the last week or so, and I think that these are sticking for at least for now. Anyway, the derivative of arcsine is 1 over 1 minus x squared. That's correct. We'll have to come back to log. I'll have to think about that a bit. But this is not a bad strategy. When you're doing a multiple choice test, just read the answers, and if one of them's kind of hard to understand, come back to it later. It's okay. Same thing for if a question is hard to understand, you can just come back to it later if you need to. Anyway, so the derivative of arctangent is 1 over 1 plus x squared. That's correct. Derivative of cosecant is negative cosecant cotangent. That's correct. Derivative of tangent is secant squared x. Derivative of cosine is negative sine. That leads me to believe that this is the incorrect statement. Derivative of log base a of x is natural log a over x. Let us go back to our board and see. So we're back at our whiteboard now, and we're going to check. So we want to know the derivative of the log base a of x. I think that's the right problem. So we're going to use a log rule that I don't know, maybe you guys haven't seen this one for a while, but we can divide up the log base a of x as the natural log of x over the natural log of a. Since we want the derivative of log base a of x, and this is equal to log base a of x, we just take the derivative of that instead. So 1 over ln a is a constant. It comes out of the derivative. Derivative of natural log of x is 1 over x. So we get, when we multiply our two fractions together, 1 over x ln of a. And that's our derivative, which, as we can see, is not the statement in, is not the second line option in the problem. Okay, let's go to the next one. So let's suppose that y is equal to 5x cubed minus 4x squared plus 3x plus 2. And n is equal to the second derivative of y at 1. Okay, so to do this, let's find our first derivative. We get y prime equals 15x squared. All right, need the minus 8x plus 3. Sorry, 8x plus 3. That's not a squared, that's just a glitch, a typo. Okay, so here's our first derivative. Here is our second derivative. Y double prime is equal to 30x minus 8. And then we want to know what is the second derivative at x equals 1. That gives us 30 minus 8 equals 22. So let's look back at our problem. Well, 30 minus 8 is a number between 20 and 30. So that's the option that we want. You see words, no calculus. See words, no calculus. What does that mean? So okay, so we're just working through some problems, and I hope that they're all showing up on the screen. My Twitch stream seems to see it. And when I look at my live stream on YouTube, that seems to show it as well. So I'm a little confused, but I'm going to assume that you guys are able to see me. Anyway, we want to find the derivative of capital F of x, which is equal to lower f of x of lower f of g of x. And then we have a whole bunch of data points. So the first thing we want to do, we're asked find capital F prime of 2. So we're first going to just find the derivative of capital F. So capital F was equal to little f of little g of x. That means that capital F prime of x is equal to little f prime of g of x times g prime of x, like this. But that means, like, now that we're asked to find f prime of 2, capital F prime of 2, that's going to equal f prime of g of 2 times g prime of 2. So let's look at our problem statement again. We need g of 2 and g prime of 2, which are 5 and 4 respectively. So g of 2 is 5, g prime of 2 is 4. Let's go back to our paint. We say that this is equal to f prime of, this one was 5, the other one was 4, and now we have to know what f prime of 4 is. And looking back on the other sheet, f prime of 4 was 0. This is equal to 0 times 4, which is equal to 0. And that is our answer. So wait, did I switch these? G of 2 is 5, f prime of 5 is 7. Sorry. F prime of 5 equals 7. So we get 7 times 4 equals 28. Okay. So, and that is an answer here. Okay, let's look at the next problem. Okay, so this problem is one of the free response questions. Let's see how this goes. Okay. There we go. So we want to find the critical numbers of this function on this domain. So we have f of x equals natural log of x over x squared. The domain is 1/2 to 5. We want to find the absolute max and absolute minimum values, if they exist. Well, they will exist, because this is a continuous function on a closed interval. Continuous functions on closed intervals always have a maximum and a minimum by the extreme value theorem. So what we need to do is, the extreme value theorem says there will be a max and there will be a min. Fermat's theorem says that those maxes and mins can only happen at places where the derivative is 0 or places where the derivative is undefined. And we'll take the convention that derivatives do not exist at endpoints of intervals. The reason we're going to take that is because since we are cutting the function at 1/2 and at 5, the function doesn't exist on the other side of 1/2 and the other side of the 5. And that means that you don't have a two-sided limit, which is how we define the derivative. So we don't have a derivative on the endpoints. That might have sounded complicated, but the point is that if we have a maximum, it's either going to happen where the derivative is 0, where it's undefined, or at an endpoint. So we'll find all of those things right now. So the derivative, f prime of x, is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. We're going to cancel one of these x's out of the top and the bottom. Now this x also cancels with this one, so we just get a 1 here. So we get f prime of x is equal to 1 minus 2 natural log x over x to the third. Where is this undefined? X equals 0. Where is this equal to 0? Well, our roots are going to be when 1 minus 2 ln x equals 0, which is the same as 1 equals 2 ln x, which is the same as ln x equals 1/2, which is the same as x equals e to the 1/2, or the square root of e, depending on what is easier for you to write. Okay, so we need to check all of our critical points, which are square root e and 0. We have to check our endpoints, which are 1/2 and 5, to figure out whichever one of these is the largest is the max, and whichever one of these is the smallest is the min, with one exception that we have to say to them. 0 is not between the endpoints. That means we throw it out. It doesn't matter. We want to find the maximum on this closed interval. This isn't in the closed interval, so we get rid of it. It doesn't matter. It'd probably be the minimum if it did matter, but it doesn't. Hello, World Noob. Thanks for subscribing. Okay, so we want to check out f of the square root of e, which is going to be natural log e to the 1/2 over e to the 1/2 to the 2. The 1/2 and the 2 cancel. E and the ln cancel. We get 1/2 of e. Sorry, 1/2 of 1 over e is what we get after we simplify. We want to check f of 1/2. That's going to be natural log of 1/2 over 1/4, which is going to equal -4 ln 2. This is a negative number. So in particular, this one is bigger than this one, because this one is a negative number and this one is a positive number. And we also get f of, oh, you can't read that part of the screen. F of 5 is equal to ln 5 over 25. Okay, so ln of 5, well, ln of e squared is 2. E squared is about 8. So ln of 5 is less than ln of 8, which is about the same as ln of e squared. So this here is going to be less than 2 over 25. This one here is going to be about 1/5 or so. This here is much smaller than this one. So this is our max. This one here is our min. Okay, so So yeah, you guys have any questions? If you do, you can feel free to send them to my email. Oh, here's a question. Okay, so let's take a look. We have question 13. They drop an x in the denominator when it should be the denominator squared. This is what we're looking at. I'm a little confused what your question is. So the email says, in problem 13, they drop an x in the denominator when it should be the denominator squared. Not entirely sure what... Okay, this is what we were doing for problem 13. I think that a typo that I had? Is that what the question is? Oh, okay. So, yeah, so it seems like I did not have a typo. Someone else had a typo in a previous review. Okay. Let us get back to the problems at hand. Let's see. We want to, in this case, we want to prove that the derivative of arctangent is 1 over 1 plus x squared. So we want to prove this. Derivative of arctangent of x equals 1 over 1 plus x squared. So the first thing we do is we're going to name arctangent. This part here, we're going to call it y, just because that'll give us the ability to do the manipulations we need to find the answer. There we go. Y equals arctangent of x. Had a little trouble of writing that, but not too much. Okay. So, now that we've done this, we're trying to find arctangent of x's derivative. So we can't just take the derivative here. We have to change the expression somehow into something else that we know how to solve. So the one thing that I can think of to do is we take the tangent of both sides. Get tangent y equals x all by itself. The tangent and the arctangent will cancel. Like so. Okay, so now that we have that, we know how to take the derivative of tangent y, and we know how to take the derivative of x. So we get secant squared y equals 1. And that gives us y equals cosine squared of... Sorry. We forgot to do our chain rule. Secant squared y prime equals 1. That gives us y prime equals cosine squared y. Dividing by secant is the same as multiplying by cosine, so we do that, we get this. We've now solved for y prime. We know that y equals arctangent x, so we go cosine squared of arctangent of x. Now, from here, this type of a problem is one that we solve by doing a diagram. I'm going to do my diagram in blue. Draw a nice little triangle. Now, with this triangle, we're going to have to label one of the sides, one of the angles, and we're going to label it using this equation here. The angle will be whatever's inside our trig function. That blue-purple color is actually really hard on the eyes, isn't it? I'm going to not write any more in that. So the thing inside of our trig function is our angle. And then the trig function here is tangent. So we're going to look at the appropriate ratio for tangent, which is going to be opposite over adjacent. And we're going to let that ratio equal x, because that's what this is. This ratio equals x. So we need to divide this side by this side and get x. The easiest way to do that is x and 1. X divided by 1 equals x. That gives us the right ratio between the two sides. We could use 2x and 2 or 5x and 5. That would be fine too, because when you divide this side by that side, we need to get x. So we do that. Now we're looking for, now that we've set up this triangle, we're looking for the cosine of this triangle. Cosine is the adjacent over the hypotenuse, so we need to figure out this side. Pythagorean theorem says that that's going to be 1 plus x squared. And so now, when we simplify, we get the cosine is 1 over the square root of 1 plus x squared. But we want the square of the cosine. So we're going to square this. This square and that square root cancel. We got 1 over 1 plus x squared. That is the derivative. Okay, so, and we can check that against the question, because the question actually gave us the derivative. They just wanted to show why this is the derivative, but they were kind enough to give the derivative to us. Okay, so we have that. Okay, so the next question, show that this equation has exactly one root or one solution in the interval this is interval -1 to 1. Okay, so let's get that one set up. First thing that we're going to do is we're going to define a function f of x equals 2 to the x plus 3x. Okay, this function is an exponential plus a polynomial, so it's continuous everywhere and differentiable everywhere. So the intermediate value theorem and the mean value theorem are both of their conditions are attained, I guess. Valid. They're both valid theorems because f is continuous and differentiable. So okay, so we're going to go here. Since f is continuous everywhere, the intermediate value theorem applies. F of, I think that the interval we're looking at was -1 to 1. Yes, let me write that somewhere. Okay, so we recall that our interval was -1 to 1. F of -1 is equal to 2 to the -1 minus 3, which is equal to, I guess, -2.5. F of 1 equals 2 to the 1 plus 3, which is equal to 5. This one is bigger than 0. That one is smaller than 0. So by the intermediate value theorem, there exists a solution between -1 and 1, or x equals -1 and x equals 1. That proves that there is a root. Now we do the other part, which is prove that there is, that was a pretty crooked line there, prove that there cannot be two. So we're going to do this as a proof by contradiction. We're going to assume that there are two roots and show that that leads to bad things happening. So suppose A, B are roots of f. Since f is continuous and differentiable everywhere, and f of A equals f of B equals 0, there exists C such that f prime of C equals 0 by Rolle's theorem. Okay. Okay. We need more space, so we deleted some things. Okay, so my paintbrush isn't working. Oh, I understand. Okay, so f prime of x is equal to, I deleted what my function was. I think it was 2 to the x plus 3x. Yes. So this will be 2 to the x ln 2 plus 3. The derivative of an exponential is that exponential times the natural log of the base. Power rule applies to 3x, giving us 3. There's our derivative. So that means f prime of c, which is 2 to the c ln 2 plus 3, should equal 0. But this is a positive number. This is a positive number. This is a positive number. You can't add two positive numbers and get 0. So this is a contradiction. So there can't be two roots. Okay, and that might seem a little strange. How did I go from this statement to this one? Well, here's the thing. In mathematics, whenever you get a contradiction, a false statement, that meant that one of the things you assumed was false. Anytime you get a false statement, that means that something you assumed was false. We got the false statement that a positive plus a positive equaled 0. That's a false statement. So we go back to the last thing that we assumed, which in this case was suppose A and B are roots of f. That was the last time we made an assumption. Everything else was logic. It had no assumptions. So that means that this statement here has to be false. Well, what does that mean? Well, that means that you can't have picked two different roots of f. And that's how it goes. Okay, so let us move on to another question. You guys still having fun? I have 40 pages of problems to get through. So far we're on page 10. I don't think I have the stamina to last 40 pages. But if you guys are enjoying this, then I'll keep going. Okay, so the next question. A ball is dropped from the top of a tall building at a point that is 1,296 feet above the ground. The height h of the ball Oh, thank you, Hakar. Sorry. The height h of the ball above the ground is given as a function of time t, like so. So let's see. We have h. Oh. H. I don't want red ink. I want black ink. So h of t equals 1296 minus 16 t squared. The first thing we want to do is write an equation to represent velocity. Second thing we have to do is find acceleration at 7 seconds. Third thing we have to do, after how many seconds does the ball hit the ground? So find time at impact, and D is what's the velocity in the ball when it hits the ground? V at t impact. Okay, so part A. We're just asked to find the velocity. So the velocity is just the derivative of the height. Derivative of a constant is 0. Derivative of negative 16t squared is negative 32t. So V equals negative 32t. That's part A. Check that one off. Okay. The next part, part B, that's usually the part after part A. This one says find the acceleration at time t equals 7. So the acceleration is the derivative of the velocity is negative 32. We plug in 7 for t. Hey, look, 32 is a constant. Doesn't change. The acceleration at time 7 is equal to the acceleration everywhere. We're done with that one now. Check that one off. Okay, time of impact. How do we find this one? Well, the time of impact is going to be the time when the height is 0. So let's find out where the height is 0. So we want 0 to equal the height function, which is 1296 minus 16t squared. I have a feeling we can cancel out a 4. Let's do that. So that's going to be 300 plus 24 minus 4 times t squared. Looks like we can cancel out another 4. Let's see, we have 75 plus 6 is 81, right? Minus t squared. Well, if this is equal to 0, that means that 81 equals t squared, so t is equal to plus or minus 9. But we're going to throw out the minus because at time t equals 0 is when we're dropping the ball. So the equation isn't going to be working for us before we drop the ball. I think we were dropping the ball. Yeah, ball is dropped at time t equals 0. So, I mean, the equation only works while the ball is falling. The ball isn't falling before we drop it. So, t equals 9. Okay, so that is the time of impact. We'll cancel that off of our list. And now we have the last one, part D. The velocity at the time of impact. Well, the time of impact is 9. The velocity is negative 32t. So v at time impact is equal to negative 32 times 9, which is some number. I think that it's, what, 200 and... what is it, 288 negative? If it's not, that's just arithmetic. That's not calculus anymore. I feel kind of scared doing math in my head right now. Okay, so let's see. Next problem. Find the derivative of the function. We have, our function is g of x equals 1. Oh. I think I messed up Twitch for a second. Here we go. Okay. G of x is equal to, there's 1 plus sine. One plus x squared to the cosine. 1 plus x squared to the cosine x. Here we go. We have this now. Now we want to find the derivative. We have a variable in the base. We have a variable in the exponent, so we cannot use either the power rule or the exponential rule. We're going to have to use logarithmic differentiation, which is totally fine because logarithmic differentiation isn't scary. We just take the natural log of g and the natural log of the other side. Hey, look. Now we have the natural log of something to a power, so we can take the power down as a coefficient. We get ln 1 plus x squared. Great. Now we take the derivative of both sides. G prime over g is equal to derivative of cosine is negative sine x times ln 1 plus x squared. That's the derivative of the first times the second. Now we're going to add the first times the derivative of the second. Well, what's the derivative of a natural log of 1 plus x squared? It's going to be 2x on the top and 1 plus x squared on the bottom. We get this. We multiply by g on both sides. We get g prime all by itself, which is what we were looking for in the first place. By the way, g is equal to 1 plus x squared to the cosine x. So by multiplying by this on this side, those two things are equal. That's g written as just a g. This is g written out as a function. Now we solved, we have g prime equals all of this, and that solves our problem. Okay. So we are on to our next problem. Oh, did I not show that to you guys? I don't think I ever switched cameras. Oh no. You guys see it now? I am sorry. I did that totally off camera for you guys. I'll just talk through the steps then. Okay. So the first line is me just copying down G again, and the pen acting up really strangely and putting dots everywhere. The next line is me taking the natural log of both sides of my equation, and then using the log rules to simplify the right-hand side of the equation. The third line is me taking the derivative of both sides. ln g's derivative is g prime over g. And then the derivative of cosine x times ln of 1 plus x squared is everything in between these parentheses that I am hovering over right now. So I get g prime over g equals this, and if I just multiply both sides by g, I can cancel out the g's, get g prime all by itself. Notice, this is g. That is also g. And we've solved it. Okay. So, there we go. And now it's time to look at the next problem. Okay. So, we have f of x equals x e to the x. We want to find the first few derivatives, and then find a general function for the derivative. Okay, so I will not forget to switch the camera over this time. So the camera is switched over, and we will solve this problem. So we were told to find the first 3 derivatives and then find a general formula for the derivative. So let's see what that looks like. Well, the first derivative is going to be the derivative of the first times the second plus the first times the derivative of the second. Not so bad. Second derivative. Derivative of e to the x is itself. Derivative of x e to the x, well, notice that this is just this. So that means that our derivative is going to just equal e to the x plus x e to the x. But then we have 2 e to the x's that can add together give us 2 e to the x plus x e to the x. Third derivative. Well, derivative of 2 e to the x is just 2 e to the x. Derivative of x e to the x is, well, again, this part here is equal to this. So this thing's derivative is just this. So let's write that down. We get plus e to the x plus x e to the x, which simplifies as 3 e to the x plus x e to the x. And in general, whatever derivative we're on, notice we get the zeroth derivative is 0 e to the x plus x e to the x. The first derivative, 1 derivative, is 1 e to the x plus x e to the x. Second derivative is 2 e to the x e to the x. In general, we're going to get n e to the x plus x e to the x. This will be our general derivative. Whatever derivative we want to get, this is the formula for it. And that's not too bad. So let's look at the next question. Okay. So we have this cone here, and I'm going to draw it on my paper. Cone. Gosh, that is a terrible cone. You'll get to see it in just a moment. This water is flowing into a tank in the shape of an inverted cone at a constant rate of 8 cubic feet per second. So that means the derivative of the volume of water with respect to time is equal to 8. Okay, so, well, what does that mean? So, that means that we're getting 8 cubic feet of water every minute. It means that dV dt is equal to 8. Because the tank is built in such a way that the radius is 1/2 of the height. Okay, so let's write that down as well. Radius equals 1/2 height. And then we also get that we're asked how fast is the height of the water increasing in feet per minute. So we're looking for dH dt, the derivative of height. Okay, so now switching over to our whiteboard. here we have all of the information that we need to solve the problem. We have the volume is equal to pi thirds r squared h. We have dv dt. We have r equals 1/2 h. What we can do now is we can, since we want dh dt, and we have dv dt, what we want to do is get rid of this r. And we'll do it using the substitution we were given. We get v equals pi over 3 h over 2 squared, because that's what r is, h over 2, and then r squared means that we square it here, h over 2 times h. So we simplify, we get pi h cubed over 6. This is our volume to height equation. We take a derivative, we get dv dt equals 3/6. So the 3 and the 6 will cancel after the derivative, giving us pi halves h squared dh dt. We know this is 8, so we go 8 is equal to pi halves h squared. What's h? Oh, I guess we didn't quite copy everything over. Let's look back at the problem and see what else we're need. Height of the water is 4 feet. Okay, so the height of the water is 4 feet. Let's write that in here. Height equals 4. That means that when we look back over at this, we get 4 squared dh dt. Now let's see. 4 squared is 16. So 8 and 16 cancel, leaving a 2 there. Half and 2 cancel like that. And then we just solve for dh dt. Right now we have 1 equals pi dh dt. Dividing both sides by pi gives us dh dt equals 1 over pi. Actually, the bottom of the page is a little bit higher than I anticipate. Let's consider this all scratch paper and then do it a little bit neater. Let's see. Here is our cone. Can't draw a cone, can I? There we go, cone. Height equals 4. dv dt equals 8. R equals 1/2 h. And volume equals pi thirds r squared h. All the steps written out nicely. Looks like this. We do our substitution. We get pi over 3 h squared over 4 h. I think I might not have squared the 2 when we did it the other time. Fortunate. B prime is equal to, we get pi thirds times 3h squared dh dt times 1/4. 3's cancel. We get 8 equals pi 4 squared dh dt. One of the 4's cancels, the other 4 cancels to leave a 2 there. 2 over pi equals dh dt. Yeah, sorry, there was a typo. Last time I forgot to square the 2 in the denominator. So this ended up being a 4. 2 squared is 4. Okay. Great. So we get 2 over pi equals dh dt. Let's look at our next problem. We're done with the first group of problems. Are we all doing okay? Do we want to keep going? I'm going to wait just a moment for people to respond. Question is, do we feel like we're ready to take the exam? And if we're not, then we'll keep going. And if no one answers, then we'll assume that we feel okay. And we'll get some sleep and be ready to take the exam on Monday. Well, I think that means that we are done for tonight. Hope that you enjoyed the last hour and a half of calculus problems, and we will, I guess to my students, I'll see you all next week. Good luck on the exam, and please subscribe to the channel or follow my Twitch channel, and you'll see other videos that I'll do in the near future. So, have a great day. Bye.